All right, so today's lesson is going to be on rational functions and asymptotes. This might be a new type of function for you guys that you haven't learned about yet. It might be something you're familiar with. Asymptotes is probably a pretty new word for you also. So right here is the parent rational function, f of x equals 1 over x. And the big key with a rational function is it's a fraction that has variables in the denominator. So when you see that variable in the denominator, you're talking about a rational function. The issue again is that we can't divide by 0, so it makes us have some interesting shapes to these functions. So let's plug in some numbers for x right here and just see what kind of function this looks like. So let's plug in 1. We can't plug in 0. Plug in 1. 1 over 1 would be 1. Plug in 2. Plug in 2. 1 over 2 is a half. 3, 1 over 3. 4 is 1 over 4, and so on, right? Now, let's plug in some negative numbers. So let's plug in -1. Actually, let's plug in some fractions also. Before, let's pretend we don't have 5. Let's plug in some fractions. So let's say we plug in 1/2. Well, 1 divided by a half. Okay, so let's think about 1 divided by a half. Remember we say multiply by the reciprocal. So really we're multiplying by 2 instead of dividing by a half, so that's 2. All right, we divide by a third, that's going to be 3, right? So you can kind of see what happens. It's like it flips the fraction around, right? So now let's plug in some negatives. So you plug in -1. All right, so that's -1. You plug in -2. Well, that's -1/2. You plug in -3. That's -1/3. Right? Now you plug in some negative fractions, -1/2. Well, now you're going to get -2. Plug in -1/3. Now you're going to get -3. All right, plug in -1/4. Now you're going to get, -4. So you can kind of see the pattern we got here. Let's plug in something a little bit bigger. Maybe let's plug in like -10. That would be -1/10, and plug in +10. So it'd be +1/10. Okay, so let's graph these now and see what the graph's going to look like. Okay, so I got kind of a big graph here. So 1, 1 is going to be right here. We got -1, -1 was one right here. When we plug in 2, we get a half. Plug in 3, you get a third. Right, plug in 4, you get a fourth. 5, you get a fifth, right? And so you can see what's happening. Those are going to get closer and closer down here. And again, you get out to 8, 9, 10. Well, now you're getting into a tenth, so it's very close to the x-axis. Of course, when you plug in a half, we got 2. We plugged in a third, we got 3. We plugged in a fourth, we got 4, and so on and so on and so on. So again, you see that's also going to do the same thing. It's going to get closer and closer right there to the y-axis. Okay, now on the negatives, plug in -1, we got -1. You plug in -2, you get -1/2. Plug in -1/3, you get, -3, you get -1/3. -4, you get -1/4. So the same thing is going to happen over here on the negative side. And then also if you plug in -1/2, you get -2, -1/3, you get -3. And so you can see that that's going to do the same thing right here. Okay, so this is an interesting shape of the graph. And essentially what's happening is we get what's called an asymptote. Okay, an asymptote is a line that you approach but never really get there. Okay, so we've got a vertical asymptote right there, and we get a horizontal asymptote right here along the x-axis. Okay, so those are lines that we're never going to touch. We're going to get infinitely closer to them over time, right? But we're never going to get there. Okay, so as we go towards, as x approaches positive infinity, f of x or y is going to get closer and closer to 0. But it's never going to get there. It's just going to approach it. It's never going to touch it. Okay, as we get closer and closer to 0, coming from the positive side, then f of x is going to approach infinity. All right, so you can see that right here. As we get closer and closer to 0 coming from the positive side, we're going to get closer and closer to infinity. All right, so that's a situation where you have an asymptote, right? And you'll see this notation sometimes. You'll see as x approaches infinity, right, f of x approaches 0. Okay, and then also on the positive side, we could say as x approaches 0, and then you'll see a little plus. That just means as it approaches 0 from the positive numbers, as opposed to approaching 0 from the negative numbers. So approaching 0 from the right, then f of x is going to approach infinity. And on the left one, you can say as x gets closer to negative infinity, so as you go further and further left, f of x is going to get closer and closer to 0, right? Because as we go further and further left right here, we get closer and closer to 0. And as x approaches 0 from the negative side, or from the left, f of x is going to get closer and closer to infinity. Okay, so might see that some of that notation. It's important to understand like what this means. You see the 0 with a plus and 0 with a minus. That just means you're coming towards 0 from the positive side, or coming towards 0 from the negative side. Okay, so let's look at, now that we understand kind of what an asymptote is, finding all the asymptotes of the graphs of these functions, okay? So in order to find the asymptotes, all you have to do is set the denominator equal to 0. You're going to have an asymptote at anything that makes you divide by 0. So for this first one here, let's set 3x squared plus 1 equal to 0. All right, and then we will solve this. So we subtract 1. So we got 3x squared equals negative 1. All right, and then we would divide by divide by 3, and we get negative 1/3. Why am I dividing by negative? That's a positive 3. So we get x squared equals negative 1/3. And then we would take the square root and square root. Okay, so right here we get x equals plus and minus. Now, the important thing right here is that we're going to get something that's imaginary. Right, we got the square root of 1/3, which I'm going to take the time to simplify, but we get an imaginary. So that means that we're not going to have any vertical asymptotes. Okay, so for this one, no vertical asymptotes. All right. Now, to find the horizontal asymptotes, right? So if you want to find the horizontal asymptotes, there's 3 situations that could happen. What we're going to look at is the degree of the top compared to the degree of the bottom. Okay? If the top is less, the degree up top is less, and the bottom one is more than the one up top, okay, then your horizontal asymptote is going to be at y equals 0. All right, so that's one situation that could happen. All right, now if they're the same, so the top is the same degree as the bottom, okay, then your horizontal asymptote is going to be your lead coefficients. So whatever A is over B, okay, where A, is the lead coefficient on the top, and B is the lead coefficient on the bottom. So just whatever the lead coefficients are, you just write that as the fraction, and that's going to give you the horizontal asymptote of your function. Okay, if the top is more, the top is a higher degree than the bottom, then you have no horizontal asymptotes. Okay, so there's none. So that's the 3 situations that could happen that you need to be aware of. So looking at this problem right here, which situation is this? Is the degree up top less, the same, or more? Well, up here the degree is 1, down here your degree is 2. So up top it's less. So that means we're going to have a horizontal asymptote at y equals 0. All right, so and you can graph that, and you can see that the graph is going to not have any holes in it, anything that's approaching vertically, but horizontally across the x-axis, the graph will approach the x-axis on both ends. All right, now let's look at the second one. Okay, so to find your vertical asymptote, set the denominator right here equal to 0 and solve. No idea why I'm writing it equals. So that's minus 1. So we're going to add 1, add 1. So I got x squared equals 1. Take the square root, and you put plus minus. So x equals plus and minus the square root of 1 is 1. All right, so we're going to have vertical asymptotes at x equals 1 and x equals negative 1. All right, so those are 2 of our verticals. Now to find the horizontals, determine the whether the degree up top is the same, is less, or is more. So for this one, the degree up top is 2, it's squared, and the bottom is 2. Okay, so it's the same. So it's this situation right here. So what we're going to look at is the lead coefficients, right? Like I'll show you right here. The lead coefficients on each term. So right here, the lead coefficient is 2. Down here, the lead coefficient is understood to be 1. So that means that we're going to have a horizontal asymptote right here at y equals the coefficient over the coefficient, 2 over 1, which is 2. Okay, and you can graph it and see that you're going to have vertical asymptotes at 1 and -1, and a horizontal asymptote at 2. All right, so go ahead and pause the video and try these two down here so you can figure out what are the horizontal and the vertical asymptotes. So for the first one, you're going to set x squared equals 0 and solve. Take the square root of 0, you get 0. So you have a vertical asymptote at x equals 0. The degree up top, right, is 0 because there's no x's. So the degree up here is 0. On the bottom, your degree is 2. The degree up top is less, which means you have a horizontal asymptote at y equals 0. So that's all your asymptotes for that one. B, you've got to set x squared minus 4 equals 0. You add 4, take the square root. So you've got vertical asymptotes at x equals 2 and x equals -2. And then the degree up top and bottom are the same, right? The degree on top is 2, the degree on bottom is 2. So you look at the lead coefficients, 1 over 1. So your horizontal asymptote is at y equals 1. All right, so to move on and talk about when you might have a hole in the graph as opposed to an asymptote. So a hole is where, you know, there's a break in the graph to where you can't use a number, but it doesn't necessarily have an asymptote at that number. It just has a hole right in the middle of the line. The line stays on its path, it just has a hole in the middle of it. Okay, so right here, what we want to look at is factoring these two functions. Okay, so before you determine asymptotes, you always want to factor the top and bottom of the function if possible. The last two, we couldn't factor anything on top and bottom. So this one we can though. We've got x squared plus x minus 2. So we can factor that using xbox. We'll multiply it to be 2 and subtract it to be 1. 2 and 1. So we got x and 2. We got x and 1. We're going to use a plus on one of them. So the big number gets the plus. So this simplifies to x plus 2 times x minus 1. Right, then on the bottom, we're going to factor it also, x squared minus x minus 6. So we factor that, we'll multiply it to be 6 and subtract it to be 1. That's 3 and 2. So we got x and 3, x and 2. We're going to use a minus on one of them, so minus goes on the big, plus goes on the small one. So we get x plus 2 times x minus 3. Alright, so now here's what ends up happening. Notice that we have the same factor on top and bottom, x plus 2 over x plus 2. So whenever you have factors on top and bottom, pretend, imagine they were numbers. If it was just like 2 times 3 over 2 times, 5. Well, those 2's can just cancel out, right? And you're just left with 3 over 5. Same thing whenever they're polynomials and you factor them. If you get the same factor, those factors can cancel out. All right. So now your function really simplifies down into just x minus 1 over x minus 3. So your graph is going to look like that function, x minus 1 over x minus 3. But you're still going to have asymptotes and holes in the graph, right? So you figure out that the things that make the bottom 0, when I set this equal to 0, I'm going to get x equals 3 and x equals -2. Those two values will make the bottom 0. Okay? But what you got to realize is the one that cancels, which was the x plus 2, okay, so this one right here that canceled out, you don't have an asymptote at that. Right there you have a hole. Okay? The one that doesn't cancel has an asymptote. So we're going to have a vertical asymptote at x equals 3, and we're just going to have a hole in the graph at x equals -2. So the line's going to, basically at 2, it's going to continue on whatever path it's on. But once it gets to 2, it's like there's a hole right there, and then it just keeps on going. As opposed to at 3, you're going to get an actual like asymptote like that or something. All right. So, of course, I drew that backwards. I guess it would be more like this. You'd have your asymptote will be out here at 3 somewhere, and then it'll be coming towards the -2. You get a hole, and then it'll go like that, something like that. I don't know. I haven't graphed it, but that's the idea. You're going to have an asymptote out here at 3, going up like that, but then right here at -2, there's a hole in the graph. Okay. So anytime your factor cancels that's on the bottom, that factor the thing that makes the bottom 0 that cancels out, it's going to be a hole. The one that doesn't cancel is still going to be an asymptote. So you guys try to figure out this one, figure out what are the holes and what are the asymptotes right here. All right, so right here you can see what's going to happen. We factored the numerator. It's a difference of squares. So x squared minus 25 is really x squared and 5 squared. So we can rewrite it as x plus 5 times x minus 5. On the bottom, you've got a GCF of x. So you take out x, that leaves x plus 5. So you got x plus 5 on top and bottom. Those are going to cancel out. So on top you're left with x minus 5, and on bottom you're left with just x. No, you cannot cancel the x on top and the x on bottom right here. Okay, you can never cancel a term if it's attached to another term by plus or minus. That x is attached to that 5 with the minus. Okay, so you cannot cancel the x's in that situation. You can cancel factors, right? So if the minus 5 wasn't there and it was x over x, yeah, those would just cancel out and be 1. But that x and that minus 5 are attached by the minus sign. Any plus or minus attaches those two terms to be one factor. Okay, you got to cancel factors, not terms. Okay, so once we cancel the x plus 5 and the x plus 5, we see that if we set those two equal to 0, set x equals 0 and x plus 5 equals 0, then we get problems in our graph of our domain at x equals 0 and x equals negative 5. We can't plug in 0 for x and we can't plug in negative 5 for x because it'll make us divide by 0. Well, the x minus 5, x equals negative 5, that 0 canceled out, right? Those factors canceled. So that we're going to have a hole at x equals negative 5 of our function, but we're going to have an asymptote at x equals 0 because that didn't cancel. And if you graph this, then you can actually see the graphs. All right, and I'll show you a picture right here on this next one. So on this last problem, let's find the asymptotes, the holes, and the x-intercepts. So now we're going into x-intercepts. We'll start with the x-intercepts since it's the new part. So to find the x-intercepts now, you're going to set your numerator equal to 0. To find the asymptote, the vertical asymptotes, you set the denominator equal to 0. To find your x-intercepts, you set the numerator equal to 0. So x equals 0. Okay, great. So this is an x-intercept. That's it. It's solved already. I don't have to do anything else to it. So this is an x-intercept. Now let's go through the process of finding the asymptotes and the holes. So we're going to factor the top and bottom. Top's already factored. The bottom we would factor into x and 2 and x and 1. And we put a minus on the big number, which is the 2, and a plus on the small one. So right here you can see nothing's going to cancel. Our factor up top is x, and our factors on the bottom are x minus 2 and x plus 1. Nothing's going to cancel, so there's not going to be any holes, but we're going to have asymptotes when we set these equal to 0. So an asymptote at 2 and an asymptote at negative 1. That looks like a 7. So asymptote at 2 and at negative 1. And we said we would have a x-intercept at 0. So these are asymptotes right here. Now we graph this, you can see all this stuff on the graph of the function. All right, so you can see right here it crosses the x-axis at 0. There's our x-intercept. And we've got an asymptote right here at negative 1, and then 1 out here at positive 2. So that's where we get our asymptotes at. So I'm going to go ahead and pause the video, let you all try the next one. Again, if they cancel out, then you're going to have holes. This one we didn't have any holes, we just had asymptotes. So you try this last one, and then we'll practice. Alright, so on this last one, you go ahead and factor the numerator by taking out a GCF of x. So when you take out x, it leaves x plus 3. Then on the bottom, you would do x box, right, and you would get numbers 3 and 2. You put the plus on the bigger one, so plus is going to go on the 3, minus will go on the 2. And then the x plus 3 is canceled. So since the x plus 3 on top canceled, you're not going to have an x-intercept at negative 3. Okay, so you wouldn't set x plus 3 equal to 0 to find one of the x-intercepts in the numerator. All right? All you're going to do is set the x up top equal to 0. So when we set x equal to 0, we get, of course, x equals 0. So that's the only x-intercept. We don't get an x-intercept from this one because it canceled out. On the bottom, you've got the x plus 3 that cancels. So at x equals negative 3, you're going to have a hole. And then when you set x minus 2 equals 0, you get 2. So x equals 2, you're going to have a vertical asymptote because that one didn't cancel out. All right, so appreciate your all's time and attention. Go ahead and practice some of these problems right here. And not too many, about 12 of them. Let me know if you need any help.